Section 2.6 is going to be about the squeeze theorem and some trigonometric limits. So we're going to start out in section 2.6, writing out the squeeze theorem and talking about what it's saying a little bit. So this is going to be the squeeze theorem. And we'll write out what it says. So we assume that for x, assume the following. Assume that for x not equal c, so assume that for x not equal to c, in some open interval containing c, that we have the following thing happen. So suppose we have a function that we're going to call L of x. We use L for lower. Suppose the L of x function is always less than or equal to the f of x function. And then suppose the f of x function is less than or equal to a u of x function for some u for upper. So suppose that we have some open interval around the c value that we're talking about. And as long as you're inside that open interval, the lower function's on the bottom, it's less than or equal to the middle function, which is less than or equal to the upper function. And now suppose that the limit as x approaches c of the lower function is equal to the limit as x approaches c of the upper function. And let's say that that limit happens to be L. So they both equal L. So your lower function, as it approaches c, your lower function's limit becomes c. As x gets close to c, the lower function approaches L. As x gets close to c, the upper function approaches L. Well, then the function that's stuck in between, if this one's going to L and that one's the one below it's going to L is going to L, and the one above it is going to L as x approaches c, then the middle function's limit, the limit as x approaches c of f of x exists, and it also has to approach L. Okay. So let's just kind of draw a couple pictures here. Let's use red for L of x. Let's use this blue color here for f of x. And let's use the green color for g of x. So what we're saying is, suppose you had kind of a lower function. Let's say that we got a axes. And so what this is saying is, suppose you have a lower function, and maybe it's doing something like this. Although, and let's say that this value here is c. So this value right here, let's say, is c. So this function's doing something like that, and it may not actually happen to take a value at, it may not actually take a value here at c. So c, there might be a little hole there. It's just because the information we got about here was saying for x not equal c, is there some open interval where the lower function's on the bottom, the middle function's in the middle, and the upper function's on the top. Then the lower limit, let's say that the lower limit as x gets close to c, let's say that the y value here is L. So as the lower limit approaches L there, the upper limit, let's say it comes down, and it also approaches L, and so the upper limit comes down, hits the same spot, then if there was a function that was kind of stuck in between these two, so if there was some function, which we'll call our middle function, that was kind of trapped in between these, then if the lower function approaches L as you get close to C, and the upper function approaches L as you get close to C, then anybody trapped in the middle is going to have to also approach L. And that's basically what the squeeze theorem is saying. A couple of things, like they don't need to be lined up like this the whole time. Like you could still apply the squeeze theorem if we had something like this. Like let's say the lower function is doing something like this. And our upper function is doing something like this. Some of you probably can already see where this is going to go. And suppose we had a middle function, which is doing something like this. And let's say our C value that we're curious about is right here. So here's the C, the L is over there. So what this business about the business here about in some open interval containing C, it's saying even like while we're close to C, is there some open interval I can put around C where the lower limit is the bottom part, the upper limit is the top, and the middle function's in the middle. So we don't care that they're out of order over here. We don't care that they're out of order over there because the C value we're looking at is right here. So we only care as you get close to C, do you get everything lined up right? So we could kind of say this all over here is far away from the C value we're looking at. We don't necessarily care about it. And over here, all this stuff, we don't care if they flip over each other over there. All we're interested in is this part of the graph. And so there is an open interval over C where the lower function is the lowest, the green function is the highest, and the middle part is passing through the middle. So for that particular part of the function, they're all basically lined up like we had them here. So we could apply the squeeze function there, could apply the squeeze theorem there, even though if we look at the whole thing, they're all lined up wrong over here and they're all lined up wrong over there. All you need there to be is that there is some region, you're able to choose some open interval where if you just kind of consider the x's in that open interval, so if we just kind of look at this open interval, red function's on the bottom, green function's on the top, middle function's in the middle the whole time, and they squeeze the upper function and the lower function squeeze to L. Therefore, the middle function is forced to squeeze to L as well. If you just have them where they don't squeeze to L, so like if say your lower function is kind of like, let's say something like this, say here's C, and let's say the lower function is doing this sort of deal, and the upper function is doing this sort of deal, and the middle function is in between. You can't use the squeeze theorem here because since the limit here is approaching down here, and the limit of the upper function at this point is actually way up here, the upper and the lower function don't approach the same point, so it doesn't force the middle function to take a value. Like the middle function could be anywhere in between these two. So the squeeze theorem only works when you have these two, the lower function pinches from below, the upper function pinches from above. They both approach the same limit at C, and then the one stuck in the middle, well, I'm trapped between two things that are going to L, so it has to go to L as well. So that's kind of how the squeeze theorem that we have here, that's some examples of how it might work. And we'll work a couple examples in a minute.